Hello everyone, myself Dr. Priya Vashisht, working as an assistant professor with School of Chemistry and Biochemistry, Thapar Institute of Engineering and Technology, Patiala. I welcome you all to the lecture series of phase rule. This is the second lecture in the series of phase rule. The first lecture has already been discussed with you. So, in this second lecture, we'll be taking up in detail the concept and utility of phase diagrams, one component system, and in accordance with the syllabus under the one component system, we will be discussing water system in detail. Now, the sequential order of the lecture will be phase diagram, its introduction and definition. In the previous video, we had already discussed what is phase, what are components, what is degrees of freedom, and how do we evaluate them. Next, we will be discussing one component system, and in the category of one component system, we will be discussing water system in detail. Now, coming to the actual definition of the phase diagram, the phase diagram is a diagram that shows the conditions of equilibrium between phases of a heterogeneous system. That is, it clearly shows, it gives the conditions under which the different phases of the heterogeneous system can be present in the equilibrium. In the previous video, we had already discussed what do we mean by heterogeneous system and how do we differentiate it from the homogeneous system. And what is a phase we had already discussed in detail. The phase diagrams are constructed as their graphical representation. They are obtained by plotting one degree of freedom against the other degree. So, next coming to types of phase diagram. Types of phase diagram, first being PT diagrams, that are pressure and temperature diagram, in which pressure is taken on the one axis and temperature is taken on the other axis, and these are generally applied to one component systems. This we will be taking up in the upcoming slides of water system. Next is TC diagram, that is temperature composition diagram, and these are applied for two component systems. These will be discussed in the next video when we discuss two component systems in detail. Coming to the application of phase diagrams, the important characteristics of the substance like melting point, boiling point, transition temperature and triple point, they can be easily located and found with the help of the phase diagram. This will be more clear to you as we proceed for the phase diagram of water. Next is one component system, and the detailed system, as I already mentioned, in the category of one component system, we will be discussing water system. Now, water has three phases, namely solid, liquid and vapor. Now, can these three phases, that is solid, liquid and vapor, be present at a particular condition, or can they coexist? If answer is yes, then what are the conditions, what are the temperature and pressure conditions that are suitable under which these all three can coexist? And according to the three phases present, these three equilibria are possible, that is liquid vapor, solid vapor and solid liquid. Now, what are the pressure temperature conditions under which these different equilibria can exist or they can retain their equilibrium conditions? All these answers are given by the phase diagrams. Each equilibrium is involving two phases here, and since water is the only chemical compound involved, as I mentioned in the previous videos, clearly explained over there, that what do we mean by one component system. Whatever are the different equilibria involved, the chemical compound is only water, hence it is one component system. If we apply phase rule to this one component system, that is water system, we simply come out to be F is equal to 3 minus P. That is, degree of freedom depends on the number of phases present at equilibrium. Now, as is obvious from this box, that if phases is equal to 1, then the system is bivariant. And hence, if phases is 2, system is univariant, and if the phases are 3, the system is invariant. This bivariant, univariant, invariant system we had already discussed in the previous video. And for one component system, what do we conclude? That the maximum number of degrees of freedom is 2. Therefore, such a system can be represented by a two-dimensional diagram. This is the phase diagram of water system. You will never be told to design a phase diagram. You clearly need to understand the outcome of this phase diagram. What do the various areas, curves, regions, points signify? What information do you get from them about the behavior of the water system under different pressure and temperature conditions? How are these curves informative to us? How are these areas informative to us? And what about the points? Moreover, on these curves, if the equilibrium is there, and if we change one or the other parameter, that if we increase the pressure or decrease the temperature on a particular equilibrium, what will be the direction of the equilibrium? That will be answered by the phase diagram. So, in these phase diagrams are constructed on the basis of Clausius-Clapeyron equations, but we will not be discussing the things beyond the scope of your syllabus. Now we are strictly concentrating on what do we actually infer and how do we visualize this phase diagram. Visualization is very, very important, and we'll be taking up it in parts in terms of curves, areas and points. So when in the exams you need to describe the water system, you need to take up in the form of areas, curves, points, and very important, you need to concentrate on various definitions that will be involved. I'll keep on informing you time to time what are the important definitions that you need to concentrate upon. So let's take up phase diagram of water one by one. This phase diagram consists of curves, areas and points that really reveal the behavior of the water system. First, taking up the curves. There are three curves in the phase diagram, as we can see here. First curve is the curve AO. This AO is the curve. Next is OC and the other is OB. As is clearly mentioned, OA is the vapor pressure curve, and this represents the equilibrium between liquid water and gaseous vapor at different temperatures. This is known as vapor pressure curve or vaporization curve of water. Why? Because it represents vapor pressure of water at different temperatures. Now what do we mean by this? That along this curve OA, at any point, if we select any point on this curve, this is X, if we select any other point on this curve, along that curve, at that point, there is equilibrium between liquid water and gaseous water, and for every particular pressure, there is a corresponding one temperature only, and vice versa. So, as you can clearly see, this point Z at 1 atmospheric pressure corresponds to 100 degrees centigrade. That is, at 760 mm of mercury, the boiling point of water is 100 degree centigrade. So, this is the curve OA, that is the vapor pressure curve. As I mentioned that there are two phases present along this curve OA, and the component is one, that is water. Now if we apply the phase rule, it comes out to be F is equal to C minus P plus 2 is equal to 1. That is, the system is monovariant. What do we infer from this? that to locate the position of any point, only one variable, either pressure or temperature, needs to be specified. If you specify one, the other one gets fixed automatically. So this curve OA, it extends up to 374 degrees centigrade. As you can see, here is the point A. This is the 374 degrees centigrade temperature. This is known as critical temperature of water. What is this critical temperature of water? That beyond this, liquid water cannot exist. Now, another very important point regarding these curves, what information do you actually get about the shift of the equilibrium? If you, along this curve, if you select any point X, say, I'm going to discuss these dotted lines now, that is XY, XZ, XB and XC, what do they actually give the information? Now, along this curve, if I fix, we can select any other point also. We can select the point here also, any other point, because at all the points, this equilibrium is valid. Now, if at point X, if I keep the pressure constant and increase the temperature, the dotted line XY will be traced and the equilibrium will be shifted towards the vapor side. That is, liquid water will be converted into vapor. At the same time, if I keep the temperature constant and increase the pressure, the dotted line XB will be traced and the equilibrium will be shifted towards the liquid water side. That is, all the vapor will be converted into liquid. If we consider the other parameter now, that is keeping the pressure fixed, if I decrease the temperature, the line XC will be traced. That is, again liquid water will be formed. Last case, if I keep the temperature constant and decrease the pressure, the dotted line XZ will be traced and the equilibrium will be all vapor side. So this is how we predict the direction of the equilibrium and we get the information that how the equilibrium will be shifted. This was not possible with Le Chatelier principle as we used to discuss in chemical equilibrium. That is not applied for heterogeneous systems. So this is the detailed information about what do vapor pressure convey us. Now this OA curve, similarly the other curve is OB. This curve OB is the sublimation curve or vapor pressure curve of ice. Why so? Because it represents the equilibrium between solid water and gaseous water vapor at different temperatures. So this is known as vapor pressure curve or sublimation curve of ice. The lower end extends up to absolute zero, that is minus 273 degrees centigrade, beyond which vapor cannot exist. As we can see, I discussed previous for the curve OA also, here also along the curve OB, two phases are present and the component is 1. Hence again this curve is univariant. What do we mean again? That is, for each temperature there can be only one pressure and vice versa. As I explained these dotted lines XB, XY, XZ, XC in the previous slide, similarly on the sublimation curve, if I select a point S, at this point S, solid water and gaseous vapor are in equilibrium with each other. Now again, we can study these parameters, that is, if we increase the pressure, keeping the temperature constant and vice versa, we can study it at any point, and the same can be applied to fusion curve also. Now at this point S, if I keep the pressure constant and increase the temperature, the dotted line ST will be traced and the equilibrium will be shifted towards the vapor side. Similarly, if I keep the temperature constant and increase the pressure, the dotted line SM will be traced and the equilibrium will be shifted towards the solid side. This region is representing solid ice. And Similarly, we can explain for SN dotted curve also and SU also. So this clearly explains that phase diagrams give the answer to, if we vary one variable keeping the other constant, how does the direction of the equilibrium vary. Now this curve OC. Curve OC is the fusion curve, and it indicates the temperatures and pressures at which solid ice and liquid water can coexist in equilibrium. That is, it represents the equilibrium between solid water and liquid water at all the temperatures. This curve OC, as you can see, is tilted towards the pressure axis. It has bent towards pressure axis. This curve is of big relevance as it shows the effect of pressure on the melting point of ice, that how the melting point of ice varies with the change in pressure. Since this curve slopes towards the pressure axis, it means that the melting point of ice decreases with increase in pressure. It is inversely related, and it can be seen, it can be visualized from this. At 4.58 mm of mercury, the temperature is 0.0075 degrees centigrade. But if I increase the pressure, that is, if I raise the pressure to 1 atmosphere, the temperature is reduced to 0 degrees centigrade. So this curve shows the effect of pressure on the melting point of ice. Next, as I discussed already, 4.58 mm is corresponding to 0.0075 degrees centigrade, and as I increase the pressure, it is reduced to 0 degrees centigrade. Next is the very important point, that is triple point. As you can clearly see, all the three curves I discussed, that is fusion curve, vapor pressure curve and sublimation curve, they meet at a common point, that is triple point. All the curves meet at this common point, and this point represents the equilibrium between all the three phases, that is, all the three phases coexist at this one point, that is known as triple point. If you apply phase rule to this triple point, it comes out to be degrees of freedom are evaluated to be 0. That means the point is invariant or non-variant. The point is invariant or non-variant means that this equilibrium is attained at a specific temperature and pressure. If I say triple point, this is more than understood that it corresponds to 0.0075 degrees centigrade and 4.58 mm of mercury. If either pressure or temperature is varied even slightly away from these conditions, then at least one of the phases will disappear and all the three phases will no longer coexist. This what do we mean by invariant system? Now, as is clear from the phase diagram, the vapor pressure curve has an extension as OA prime. This dotted line OA prime, this is extension of the vaporization curve, and this is known as metastable curve. Why this is known as metastable curve and what is it representing? If using special techniques, if we can cool the water below its freezing point, this point 0 degree, this point 1 atmosphere, this temperature 0 degree centigrade corresponding to 1 atmosphere, this point is freezing point of water. At 1 atmosphere, point Z, that is 100 degree centigrade, was boiling point of water. Water can be cooled below its freezing point without separation of ice. This is known as supercooled water. Obviously, this is done with very specialized techniques that operate with ultra care. So, along this metastable curve OA prime also, the equilibrium is between liquid water and water vapor. And the equilibrium is said to be metastable equilibrium, because as soon as even a small particle of ice is added to supercooled liquid, that is, if you bring ice in contact with supercooled liquid, the entire liquid gets solidified immediately. So it is so unstable That is why it is known as metastable equilibrium. Now, it is very important to understand the difference between true equilibrium and metastable equilibrium. True equilibrium you have been studying in your lower classes also. True equilibrium exists when the same state in the system can be achieved from either direction. That if you have an equilibrium between solid ice and water, or you have between solid ice and water vapor, so you can achieve it from either direction. In context of thermodynamics, true equilibrium is attained when the free energy content is minimum for given value of variables. For example, for this system at 1 atmosphere and 0 degree centigrade. Whereas metastable equilibrium cannot be realized from either direction. It can be realized from one direction only. And as I mentioned in the previous slide, if you bring a little piece of ice in contact with the supercooled liquid, it immediately solidifies. That is, if there is a slight variation such as shock, stirring, slight disturbance, the equilibrium is disturbed. Next very important difference that we need to discuss at this point is, what do we clearly mean by triple point and critical point? The triple point of a substance is the unique temperature and pressure. Why do I mention unique? When you come to definitions, there are certain keywords you need to stress upon. The triple point of a substance is the unique temperature and pressure. Why do I call unique? Because it is clearly specified that it has to be 4.58 mm and 0.0075 degree centigrade, in which three phases of that substance coexist in thermodynamic equilibrium, giving you an invariant system. Whereas critical point is a point on a phase diagram at which both the liquid and gas phases of a substance have the same density and are therefore indistinguishable, and the point system is univariant. So this difference between triple point and critical point. Now next, if I want to shift to areas now, as I mentioned clearly, the curves OA, OC, OB, I discussed points also, critical point, triple point. We are left with the areas. Now there are three areas in the phase diagram, as you can see clearly: COB, AOC and AOB, consisting of ice, liquid water, this is ice, liquid water and water vapor respectively. All the three areas, they consist, as you can see, they consist of single phase. In this area COB, only ice is present. In this area AOC, liquid water is present. In area AOB, water vapor is present. That is, the system is bivariant. The system is bivariant. It means that I need to specify both the parameters at one point. That means to find the position of any point, it is mandatory to specify both the variables temperature and pressure along each curve, which means that to locate we need, but along the curves we needed only one variable. Now in area, if I give you an example, if I say minus 10 degrees centigrade, the pressure can be any. At minus 10 degrees centigrade, if I mention the temperature minus 10, pressure can be any. So for a particular point, I need to specify both the variables. So this is what do we mean by bivariant system. Now if I summarize all the areas, curves and points in a single table, mentioning their corresponding phases and their corresponding degrees of freedom, it can very well be summarized. This will be really helpful to you. Rather, once you go through the video, you should be able to evaluate this table on your own, that along the curve AOC, what are the phases, along the curves, what are the phases, and what are the degrees of the freedom. So this is the summarized table of already discussed concepts, and in the next upcoming video, I will be discussing up with you two component systems, simple eutectic systems. Thank you.